Okay, welcome back. In this lecture, we're going to introduce the Poisson distribution. Now, this is going to follow quite a different path to what we've had previously. So for earn models, it was all about using the idea of push forward pretty much to throw out information when we decided that we didn't care about that information. This is a much more sort of hands-on heuristic argument to get to the Poisson distribution. So what we end up with, we do actually have to check is a probability measure. Okay, so the idea with the Poisson distribution is that you've got some time interval, 0 to t, and you've got, random occurrences which occur at rate alpha per unit time. Okay, and we ask what's the probability of k occurrences? By time t. Okay, and this has clear modeling applications because, these occurrences can be pretty much anything. They could be raindrops landing in a cup, or they could be, say, insurance claims, whatever, all sorts of things. So it seems like a reasonable question. So how are we going to come at this to heuristically argue what sort of probability distribution such an event should have? What the probability of k occurrences should be. Okay, so we split 0 to t into n subintervals of equal length. Okay, and we suppose n is large enough that, the first thing is that at most one occurrence happens in each interval, and two, occurrences are independent in a sense that I'm not going to really get at from a strict point of view, but we're just going to act as if we understand what we mean here, as we did with the earn models, that you draw balls, put them back or not, and then draw again, and that there's no sort of relationship between what you draw the second time, at least if you put them back. This should be occurrences in each interval. Okay, and that's going to let us treat this as if it is actually an earn model. Okay, so we can think of each of the n intervals as a ball, and we could give them a color 0 if no occurrence happens, and a color 1 if an occurrence happens. No, sorry, that's incorrect. So, let's just get on with it. Sorry. Okay, so from this setup and from our sort of rough idea that occurrences happen at rate alpha, the probability of an occurrence in any of these intervals is going to be alpha t on n. Okay, and they're independent in the sense that we've decided well, in a sense that we're not really talking about. So then we can think of this as really just selecting out of these n intervals which ones have occurrences in them. So that's very similar to an earn model, and that's how we're going to treat it. So we're at this point, we'll model the number of occurrences as a multinomial distribution. Well, sorry, as an earn model. Sorry, I think I'm repeating myself a lot here. So we'll say the probability of k occurrences is going to be, well, for a fixed n, we would like to think that this is the multinomial distribution with n draws, with alpha t on n successes and 1 minus alpha t on n fails at k. Alright, but we only want to treat this as valid if n is really, really big. So we'll put a limit here. Now, there was something that I realized I missed previously when we were talking about multinomial distributions. So in the case that you've only got two colors, I mentioned that in that case we call this binomial distribution instead. Oh, sorry, I've messed it up here too. So we want k successes and n minus k failures. So if you've only got two possible colors, then there's a lot of degeneracy in how much information you're putting here, and we would typically actually write this as the binomial distribution. So this has this notation where now these have to add to 1, so it's enough to only record one of them. We record the probability of a success, so alpha t on n. And here, well, these numbers have to add up to n, so we only need one of them, and we look at the number of successes. Okay, so these are just a notational difference when we've only got two possible colors or two possible states, success or fail, that sort of thing. Okay, and well, we're claiming that this should be the probability, but we don't actually know that this is a probability in that, well, these limits, they may not even exist, and furthermore, we need the sum over such limits, the sum over k of such limits to be 1. So let's go ahead and verify that. Okay, so we'll calculate this limit explicitly. So this is limit as n goes to infinity of n choose k alpha t on n to the k 1 minus alpha t on n to the n minus k. Okay, let's just do what we can. Limit n goes to infinity. Well, this is n minus 1 dot 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 n minus k plus 1 divided by k factorial. This will just split it up. Alpha t to the k on n to the k. And this part we'll split as an n and a minus k. So negative k first. Okay, and well, we can use our limit laws here. So first of all, well, these two do not depend on k, so do not depend on n, so we can ignore those. This part here is going to be roughly n to the power of k, because it's sort of products of n minus 1 all the way down to n minus k, and there are k of those. So here we've got something that's roughly n to the k, here we've got an n to the k, so to leading order, those cancel out, and the other order are going to be sort of eliminated by this thing growing quicker than this. This part here, well, the only thing that changes is the n here. For n large enough, this number is going to be not near 0, it'll be near 1, and then the negative k doesn't matter, so this part is going to limit to 1, and this part we can recognize from the exponential formula is going to limit to e to the negative alpha t. So writing all that up, we find that this is alpha t to the k on k factorial times the exponential of minus alpha t. Okay. Now, okay. So, for notational reasons, if we let lambda equal alpha t, so this is in some sense the number that we should expect in our the number of occurrences in our time interval, and we let Pn be alpha t on n, well then we found that the binomial distribution with n and rho n at k converges to, as n goes to infinity, lambda to the k on k factorial exponential minus lambda, which we're going to call the Poisson distribution with rate lambda. Okay, and we should check that this is actually a probability distribution, as I've been mentioning all the time. Also note that here we had alpha as the rate previously, now we're going to call lambda the rate. We'll see the reason for that when we get to Poisson processes later in the course. So, the question is P lambda a probability distribution? Okay. Well, we're on a countable sample space. Sorry, this should really be on non-negative integers with its power set. Okay, and well, the non-negative integers is countable, so our sample space is countable, so all we have to really check is that each of these values is between 0 and 1 and that they add up to 1. Okay, well, are they between 0 and 1? Well, each one is certainly positive because lambda is positive, k is positive, and the exponential of anything real is positive. So to check that they're below 1, it suffices to just check that they add up to 1. And we have that the sum from k equals 0 to infinity lambda k on k factorial exponential of negative lambda. Well, we can pull the exponential out. Okay, but this is just the power series for the exponential evaluated at lambda. So this is just exponential of lambda, exponential of negative lambda, exponential of lambda, which is 1. And so, therefore, the Poisson distribution applied to each k is also between 0 and 1 by the reasoning I mentioned earlier, namely that these are all non-negative, or actually they're all positive, and they add up to 1, so therefore each one must be less than 1. Okay, and that confirms, yes, Oh, that's getting very curved now. P lambda is a probability distribution on Z plus with its power set. Okay, so yeah, as I've pointed out all throughout this is really a heuristic argument, which then gives us a definition for what we would like to call the Poisson distribution. The relevance of this Poisson distribution is really going to come in, well, we can pretend that our argument was all very rigorous, or we can just take this as a definition and show that it's a reasonable object to, well, a reasonable definition to have. And that's pretty much the approach that we're going to take. So we will see this pop up later in the course with relation to the Poisson process, and that's a really important process. That's when you let t vary. Okay, so there's another interesting thing that we can check is for what k is the Poisson distribution maximized, which you could essentially means what is the most likely number of outcomes that you have. Okay, and well, to figure this out, we find that p lambda of k divided by p lambda of k minus 1. Well, let's just write this out. So we've got the exponentials, those are constants, so they drop out. Everything else, we're going to have lambda to the k on k factorial divided by lambda to the k minus 1 on k minus 1 factorial. Okay, and what we end up with is lambda on k. So hence this is maximized when this the largest value of k for which this is bigger than, so this, we're looking at the probability of k divided by the probability of k minus 1. So we want to check when this goes from being bigger than 1 to when it becomes less than 1, and that's going to be when k is when the probability of k is maximized. And well, this is bigger than 1, greater than 1 for k let's think about it. Well, yeah, it's bigger than 1 for k less than or equal to the floor of lambda, i.e. Largest integer less than lambda. Okay, and then it's going to be less than 1 for k bigger than lambda. And this means that the most likely number of occurrences in your time interval 0 to t is exactly, well, the largest integer that's less than lambda equals alpha t. In other words, you're going to have roughly alpha t occurrences, which is exactly what we wanted from our heuristic. Okay, yep. Thanks for listening. I'll see you in the next lecture.